So in this video we are going to look at some infinite series, and we're going to start with an arithmetic series. And the first question we want to ask ourselves here is, are these series convergent or divergent? So we're going to try an arithmetic infinite series. And we'll just look at an example here. Let's say you had in this series 1 plus 5 plus 9 plus 13 onwards, adding those numbers up forever. And you can see that as I keep on adding, the total sum is going to get bigger and bigger. And not only does it get bigger, it gets bigger without any limit whatsoever. So in other words, if you name a very big number, I can get this series to eventually reach that number, no matter how big it is. So this is divergent, because the sum approaches infinity as n, which is the number of terms, approaches infinity. And in the other cases, even if we start with something with a negative difference, like let's say I started with 5 plus 2 plus -1 plus -4, so I'm decreasing by 3 each time. This is going to, it's not going to be a positive number, but it's going to get towards the negative end. So it's going to get a bigger and bigger negative number. So let me illustrate here. 5 plus 2 is 7, minus 1 is 6, minus 4 is 2. The next term in here would be minus 7, which will give you -5. If you subtract the next term here, which would be -10, it's going to give you a bigger and bigger negative number. Okay? So this here is also divergent, because the sum goes towards infinity as n approaches, the sum goes towards negative infinity as n approaches infinity. Now, so the main idea to get from here is that all arithmetic infinite series are divergent. If it's arithmetic and infinite, it is divergent. The more interesting case to study here is the geometric series. So I'll be very clear, this is an infinite geometric series. And we'll look at an example. We'll call this example 3. If we start out with 1 plus 2 plus 4 plus 8 plus 16, you can see onwards. So the definition here is that the first term is 1 and the common ratio is 2. And this series is going to be divergent as well, because you can see that these sums are just going to get really, really huge. And so this one is divergent. And the reason that it's divergent is that this ratio here is 2. So you're adding twice as much as what you had before. You are adding twice as much as what you added before.
So Ryan, do you have time?
So let's look at a case when it is also geometric, but the ratio is different. So what if I give you this number, this series here, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and continuing on. And if you take out your calculator and actually type these numbers in, you're going to get 1.5, 1 3/4, 1 7/8, 1 15/16, and it's going to get, the number will increase. Okay, so the number will increase, the sum will increase, but there's a limit to this. And in this case, a sub 1 equals 1, r is equal to 1/2. And if you keep on going like this, eventually you're going to approach 2. So the sum will approach 2 as n approaches infinity. And I'll explain this visually. So let's say you had, we'll call these units here. So we start out with a distance of 1 unit, and then after that we add to it a 1/2 a unit, and then after that we add to it a 1/4 of a unit, and then after that we add 1/8 of a unit. And if I make this point here 2, okay, we're never going to reach this point, because no matter how far you go, so if at first you go 1, which is halfway to 2, I want to go one more unit, but I can only go a half, so I get to here. And I would like to, so there's a half unit left here, and I'd like to go a half unit, but I only get to go a quarter of the way. And then there's a quarter of the way left, but I only get to go 1/8 of the way. So eventually, what I'm really doing is just going half the distance to the end. And if you go half the distance, there's always a half a distance left. So so this series will get closer and closer to 2, but it will never actually reach it. And let me show you, hit pause here, I'm going to show you the algebraic concepts behind it. So we'll start with the finite case, okay? And we're talking about geometric series here. I'm going to erase this so it doesn't get confusing. So from the finite case, which is what we did in our last videos, the sum is really equal to the first term times 1 minus r to the n divided by 1 minus r. Okay? Now, this is for the finite case. For the infinite case, the sum is equal to the limit as n approaches infinity of the first term. So it's the exact same thing, but because we have an infinite number of terms, we have to use the limit as n approaches infinity. But if r is between 1 and -1, in other words, this is saying if r is a fraction, okay, r is a proper fraction, then r to the n approaches 0 as n approaches infinity. So as the exponent gets bigger, this entire term, r to the n, is going to approach 0, because you're taking a fraction of a fraction of a fraction of a fraction. So because that's true, the limit as n approaches infinity of this series is really a sub 1 times 1 minus 0. Okay? Because again, this part here is going to approach 0, all of it divided by 1 minus r, which then gives us a to the first times 1 over 1 minus r. And this is the sum of an infinite geometric series.